Welcome back. This is the final video for this week, and that'll be our final video on PN junctions. So far we've been through the operation of a PN diode and analysed why the current voltage characteristic looks like it does, both in forward and reverse bias. We also derived the Shockley equation, which is at the start and also shown here. And we showed that we can quantify the amount of current flow I with respect to voltage V across the junction from knowing the material parameters, the device dimensions and the doping concentration. And we did this by showing that the devices are minority carrier devices, as it's the diffusion current that determines the current flow through the device. And we therefore needed to calculate the minority carrier concentration, as it's the gradient of the minority carriers that determines the diffusion current and consequently the current flow through the PN diode. So in practice, to calculate the minority carrier concentration, we use the doping concentration to estimate the majority carrier concentration, and then we use the knowledge that the number of electrons times the number of holes in a semiconductor, so the NP, is equal to the intrinsic carrier concentration squared. And so the ability to calculate this concentration of minority carriers is really possible using knowledge of the doping, which is a design parameter. But to get this minority carrier concentration is so important, it's very worthwhile to become familiar with the method for doing this. In other words, using this NP equals Ni squared. And also, please become familiar with the equation 31A and 31B, which enables us to calculate the number of minority carriers when a bias is applied, and therefore calculate the gradient of carriers between the depletion region and the bulk, its variation or gradient. And this is essential as it enables us to work out the diffusion current and the current flow through the diode, and using the knowledge of the semiconductor materials properties and also the device dimensions. And that's what we've really been doing. But most importantly, remember that the drift current, which dominates the current flow for majority carriers, is only really balancing out the diffusion current on the other side of the junction. So in PN junctions, it's the diffusion current that needs to be calculated. So understanding and calculating the minority carrier equations and calculations is really paramount. So although we've observed and looked at ideal diode characteristics and calculated the current according to the ideal characteristics and devices, we need to remember that in practice we can't apply infinitely high voltages to the junctions, either in the forward or reverse bias, and that's because the junctions are going to break down. So these are ideal situations, but in reality, if the junctions break down, you're going to get to an uncontrolled current flow rather than the controlled current that we can quantify according to this ideal Shockley equation. So in fact, there's three main methods or mechanisms through which the junctions will break down with a high field applied. And the first is through heat generated from high reverse bias. And this is really known as thermal instability. At high reverse bias, the reverse current that we've called IO, or the reverse saturation current, causes a considerable heat dissipation. Now remember that the number of conduction electrons varies with temperature, and different semiconductors have different sensitivities to this temperature rise or fall. And the temperature rise from the high reverse bias will increase the reverse current, and a so-called thermal runaway occurs. In other words, the temperature changes the conduction in such a way that further increases in temperature will occur. Ultimately, this is going to destroy the device operation. It's a type of uncontrolled positive feedback. So the thermal instability, you could say, occurs at a turnover voltage specific to the device and the operating conditions and the material, and it's clearly going to be less important for lower temperatures. But it is something to be aware of that isn't sort of included in the ideal diode equation. The second breakdown mechanism is a tunnelling mechanism known as Zener breakdown. And here, for a PN junction under a reverse bias, the band diagram looks something like this. And you have electrons in the conduction band here and holes in the valence bands. And because there's a reverse bias, there's a significant potential barrier, which we've already said is directed from the N region to the P region. And the reverse bias makes that built-in field bigger. And because it's quite significant, it means the likelihood of a carrier being able to overcome the barrier is really low. And so ideally, only a low current will flow across the junction. However, at very large applied bias, reverse bias, and especially when there's high doping, the picture changes and it becomes more like this, whereby there's a very high electric field, which is shown by the steeper band bending between the N and P type regions here. Okay, so in this situation, the electrons can actually tunnel from the valence band to the conduction band through the band gap, or vice versa. Okay, and the necessary conditions for this type of quantum mechanical tunneling to occur, whereby the carriers go through the band gap, is that there need to be occupied states to tunnel from, there need to be empty states to tunnel into, there's got to be a finite tunneling probability, and the momentum conservation has to be maintained. So in fact, for silicon, electric fields of around 10 to the 6 volts per centimetre give rise to a significant tunneling current. And this takes place when the doping and therefore the field in the depletion region is very high. The band gap of silicon and gallium arsenide decrease with increasing temperature, and this means that the tunneling current can occur at lower electric fields at higher temperatures, or at higher temperatures you can get more current with less voltage. In other words, the higher the temperature, the breakdown voltage is going to decrease. And so this negative temperature coefficient enables the tunneling mechanism to be distinguished from other breakdown mechanisms. And it's also worth pointing out that because the current is related to an electric field, it's now a drift current. So the breakdown current is a drift current dependent on the electric field, as well as the band gap and the tunneling probabilities. So all our derivations and assessments of the diode suggesting that the diode is only determined by the minority carrier concentration and the diffusion current is true, as long as the junctions haven't broken down. And then the final mechanism I'd like to mention is avalanche multiplication. It's also known as impact ionization. And if the electric field in the depletion region is high enough, using again a reverse bias, then carriers can gain sufficient energy to make ionizing collisions from atoms, which create these electron or additional electron hole pairs. So if a hole current, IP, is incident at x equals 0, which is the edge of the depletion region, the width, the depletion region's got a width W, then IP, the hole current, is going to increase as it goes along through the depletion region, generating more electron hole pairs. And so this means that there's going to be more current for larger depletion widths. And similarly, the electron current travelling in the opposite direction is going to increase as it goes in the opposite direction from x equals W to x equals 0. And the total of the current of the electrons and holes is going to remain constant in a steady state. One's going in one direction and one is going in the other. That's what this is saying here. So the avalanche breakdown voltage imposes an upper limit on the reverse bias for most diodes. It limits the reverse voltage that we can apply, for example, most importantly on collector voltages of bipolar transistors and also on the drain voltage of MOSFETs. And both of these transistor diodes have a key function in the operation of these transistors, as we'll be finding out in the next topic. So it's very important to realise that there is a sort of limitation to the operation. We don't need to go into the more detail of the breakdown mechanisms, but we need to be aware that there's a maximum voltage possible before the junction and the device will break down. It's also worth remembering that the different diode types have different breakdown mechanisms and characteristics, and so you usually get an increase in the reverse current with increasing temperature, and good heat sinks are therefore going to be necessary to cool the device. But as long as you're aware of which material you've got, what are its operating limitations, you can usually account for these and get a good operation of the device within the limits available. But sometimes you do need to, for example, switch the material in order to get around the problem. And again, that comes back to your data sheet where you have to be aware that different semiconductors have got different properties, different band gaps, and can withstand different bias conditions. So that brings me to the end of what I'd really like to say about PN junctions. It's all highly relevant for the two sections on transistors, not least because of the issues with the reverse bias applied to both bipolar and MOSFET transistors. But we'll start out in our next set of videos on the bipolar transistor. Okay, thank you very much.